Okay, awesome. So I was just talking a little bit about data structures and why they're important. The things you'll learn this week may come up in technical interviews. They're also concepts that will help you be successful in your career. And you'll see them even if you don't apply them directly, the patterns you see will come up in other places. This is a bit of a preamble. Because in order for a lot of this stuff about data structures and algorithms to make sense, it helps to know a little bit about how computer memory works. So as like the slide says, what we'll be learning is called like complexity analysis, or big O. And this is a big part of computer science, and it's important for software engineering as well. Because it's valuable to be able to know how long a program might take or how much space it takes up. How long something takes to run, how much memory it might take up. And really, this is about efficiency. It's not actually about like real numbers. It's sort of about like if an imaginary computer was running this algorithm, how long would it take? Not how long does it actually take. For real world software engineering, people do care about real numbers. But you just run programs and get real data for that. So this is why we care a little bit about computer memory. And computer memory is basically a bunch of slots like this. And let me get my little annotate thing here. And, you know, at the most basic level, you can imagine a bunch of zeros and ones here, right? Some binary. So each of these little slots could represent a bit. But maybe each of these slots represents more than just a 1 or a 0. Maybe it represents a block. Maybe it represents 8 bits or a byte. And so this analogy of like a long street and blocks makes a lot of sense. Excuse me. So as you all probably know, in the world of computers, everything is by powers of 2. So we can imagine 1 byte, 1 or 0, or 1 bit is 1 or 0, 1 byte, 8 bits. And here we're saying each chunk is 32 bits long, so 4 bytes. So it's not too important to worry about the exact numbers, but to just start to get a sense of this. So the interesting thing is that everything in computer memory is stored this way. So not only are, like, if we have, a city block with houses and apartment buildings on each block, not only is that stuff stored this way, but say our address book is also stored this way. So the address book can only get so big, right? Like, we may not have used it directly, but you may have encountered the concept of, like, how big an integer can we create? The way that computer memory works sort of imposes a maximum size on certain things that we can chunk up. And in Python and higher level languages, we usually don't have to worry about this. It can be interesting to run this ID function. In fact, let's do this now very quickly, just for fun. So this is the address of where that variable lives in memory as a decimal. Right, to go back to this little diagram, that number might tell us if we live in the first chunk, the second chunk, the third chunk, the fourth chunk, or so on. Hexadecimal is just another way of encoding this. The same location, just encoded in a different way. And every time we create a variable in a Python program, Python has to know where this variable lives and uses something called a lookup table, which is pretty common for programming languages, that says, hey, when I use this variable X, go to this memory location. Because, like, what really sort of the computer actually executes is not our source code. The Python interpreter sort of turning it into something lower level. And as you all may have learned, pretty much everything on a computer is standardized. And a lot of how this works is simply convention and rules. So, for example, characters, well, there's a lot of different possible characters. You all have probably heard of ASCII. There's also Unicode. Unicode is much bigger. But the point being is that we have to have, like, a standard format to take some value and encode it. And we can see over here on the right, each character, lowercase a, uppercase A. These are sort of special characters specific to the machine that we don't use a lot, but space is a character, right? All these symbols, characters, and they get a numeric code. And note that there's 127 of these. Two times two is 4, times two again is 8. Right, so 2 raised to the third power is 8. Sorry that this doesn't come up so clearly, but actually let's just do this. So 2 to the 7th down here is 128. And we're interested in powers of 2 because everything is binary, ones and zeros with how computers work. And with how memory works. So this ASCII chart goes up to 127, but also includes 0. We're indexing, so there's 128 values here total. And again, to sort of take things back, how much can we fit in 1 byte to the third, in 4 bytes, so on and so forth. So the number of possible values has to fit into some powers of 2 chunk. So for each character, regardless of whether it's the first or the last character in our list, whether we're looking at A or whatever, each character gets 32 bits. And I'm not sure if that's like how much space they actually get for a computer, for like real world encoding, but for our example, it's perfectly useful. Sorry about that. So just kind of want to get you all start to thinking about how things are stored, how much space they might take up, and how like stuff has to be chunked and organized in order to be saved in a computer. And let me pause and see if folks have any questions here.
I had a little question about the hex IDs. When you displayed that one, I was just first off, I guess how many numbers long is it a specific convention? And then second, does each number, it didn't look like any of them in that hex ID was larger than 8, but I didn't know if that was a how it works or if it was just a happenstance. But does each one, if so, represent a byte?
Oh, that's a great question. I am actually, I'm not gonna lie, I'm not super familiar with hexadecimal. So let's quickly find out. So there's an interesting chart here, but basically, right, base 2 binary, you have 1 or 0. Base 10 decimal, we have 0 through 9. Hexadecimal, meaning like that's the basic number of digits that I can represent before I have to start combining them. Hexadecimal, base 10, 0 through 9, and then 8 characters. So like 16 in hexadecimal, let's just do a quick, let's look for a quick chart. So it's not worth going into this too much. But you see the basic idea here of, hey, like once we get past 9 in the decimal system, let's start using these letters. You don't really have to worry about knowing hexadecimal or using it. It won't come up that much in the course. Occasionally it comes up in the professional world, and honestly, off the top of my head, I'm not sure what the best cases for this encoding are. But you can sort of see the advantage of to this if like we're writing a computer program. Like think about the Roman numerals problem. Think about how much work went into figuring out, what that V or that 1 represented. Well, with these 8 extra characters, we get a whole lot further with it being very explicit. And that's probably why someone came up with this. So does that help give a little context?
Yeah, it does. Thank you.
Yeah, absolutely. Great question. And again, hexadecimal, I'm not using it much on a daily basis. Not something critical that you have to know. More so, it's good to just start thinking about like, hey, like the way that the computer stores information is different from how we see it, and that there are these sort of like encodings and mappings that go on. So this all leads into arrays. JavaScript has a data type called arrays, but it's not actually a real array. It's really a lot more. It's probably a list if we were being strict about naming things. And so Python did a much better job because they named their list a list. Talking about data structures and computer memory, like an array is something a little more specific and a little more limited. And we'll talk about in a moment what that is. As you all are pretty familiar with Python lists, and that's really kind of what JavaScript arrays are. They're basically lists. I'm going to be talking about data structures a lot, and so just a note on terminology. You might hear us talk about data types, as in like the type of a variable, like a Boolean, a dictionary, a list. And so really those are like, yes, in a sense, like that those are data structures, but really if you hear people talking about data structures, it's more often talking about some more abstract examples that we'll see soon that like you can implement in different programming languages, but is a little more abstracted. That said, you'll also hear me talking sometimes about like the shape of data and stuff. And yeah, in a sense, like that is the structure of data, but really, if we say data structures, we're talking about these like specific data structures that are often taught in computer science courses that are really fundamental to how computers work. And that are it's a little it's a little less of a practical application, which I know can be a little confusing, but I think the more you see it will start to make sense. So in that vein, an array data structure, I'm not talking about JavaScript's implementation of an array, which isn't even really an array. I'm not talking about Java's implementation of an array, which actually is an array. Or any other language's implementation. I'm talking about the abstract idea of an array. And this is how computers work on a pretty low level. Um, Once you start getting into the nitty gritty, like maybe different CPUs or chipsets have minor differences in how they implement things, right? Like, so the worst, a decent metaphor might be, if you think about a car, every car is going to have an engine, it's going to have a gear shaft, it's going to have brakes, it's going to have tires. But the way Hyundai builds its car versus Ford might have some differences, but it's still useful to be able to talk about the design of a car with tires and brakes and a gear shaft and like an engine without getting into those minor details. And it's sort of similar with data structures. Like at a really low level, every computer is using arrays, and they're mostly implemented the same. Um, but that's why we talk about this a little abstractly, because if you really start getting into the nitty gritty, um, these days it's more standardized, but even still, like how the chips now that Apple makes their own chips work, like right, there might be some minor low level differences versus Intel chips or whatever. So this array data structure, this is like the most sort of fundamental building block, I would say. And the most important thing is, first of all, everything in an array has to be of the same type. Um, Second of all, when you create an array, you have to define how big it is. 4 bytes, 8 bytes, 32 bytes. You can't just keep adding stuff onto it. And we've never actually really encountered this because these higher level languages do this work for us. And the good news, again, this lecture is really more contextual in a lot of ways. Um, and the reason that we have to set an array its size is because the computer memory makes sure that the stuff in an array is actually right next to each other, right? And if you think about like a vinyl record, which is an awful sort of like how hard drives used to work before they mostly became solid state drives, like where stuff is put does matter in terms of finding it and in terms of being it next to each other. And the same for computer memory too. I'm not sure how solid state drives work, but I'm sure it's something similar. And in fact, let's see if we can find a little, maybe it's not this, maybe it's, here we go. This isn't the worst if we can make this bigger. Is this relatively readable? I know this is a bit blurry to everyone. Um, this isn't the best diagram, but like, and it's not worth going into too much detail, but like one way of thinking about like what is a computer in an abstract sense is you have tape, and the tape is chunked up, and each cell on the tape can have a symbol. And then you've got this machine, and it reads like one spot on the tape, and it does different things based on the different symbols, and it moves back and forth across the tape. And computer memory did used to be stored on tapes, right? And in some ways, like if you think about like a reel-to-reel tape player, that's not the worst analogy either. Here we go. This one might be a little bit better. So this one's a little less blurry. Um, and so maybe the symbol 0 means it gets saved in here. Maybe when you see a different symbol, it means add the two symbols that you've saved together. Like without going into too much detail, this is sort of like the abstract model of what a computer is and how it works. And again, in the real world, memory doesn't work this way anymore. But you can see how if you have stuff that's right next to each other in memory, it makes it easier to find it. It makes it more efficient. That's what I really wanted to go to this tape thing for. Because if we go back to talk about arrays, it's like if you're looking for a bunch of people's names in the phone book, if everyone's last name starts with the letter A, it's a whole lot easier because it's on the same page. But if you have to like look at one page here and then go to the end of the book to find another page, and then go in the middle to find someone whose last name starts with the letter M, that takes more time. And the thing to remember is that computers used to be slow. So that time really mattered. And today, even though they're fast, computers do so much. God knows how many thousands of operations per second, that at this really low level, like, this is like the people doing operating system work are not really worrying about this probably too much these days. Like this might be at the level of like the driver software for a solid state drive or whatever. At this really low level, that efficiency still matters. So the advantage of an array data structure is because it's only got the same thing and it's got a limited amount of size, we can put it all next to each other and then find stuff in it very quickly. So just to give an example, like in Python, we might create a list, and under the scenes, maybe what Python is having in the way that this list is stored in computer memory is actually an array. I don't know. We don't have to know. That's the beauty of higher level languages. We're trusting the Python interpreter to do that work and deal with that lower level work for us. And if you work in like a language, like a lower level language like C, some of that you have to do manually. And it can be good for learning, and maybe sometimes you get efficiency from it. But these days, things like compilers, interpreters have gotten so good that we don't have to do that work. And it saves a lot of time because, I mean, you all just worked on this assessment and did plenty of debugging. And you can imagine just how much more debugging it takes to write software at this lower level. And this term of pointer probably makes sense if you think about JavaScript, right? A JavaScript array feels a lot more like an array, but a JavaScript array is not fixed in length, and you can have different kinds of things in it. And thus it's not like an actual array data structure. But you're used to in JavaScript, you use the for loop and you set that variable I, and that's a pointer. And that whole style comes from when you're dealing with real arrays. And the pointer points to the index of the array, which if this was like actually an array at that low level would be like the memory address of where this value actually lives in memory. And so it's this part might sound a little funny, but I think the thing to keep in mind is like if I know my array is 5 bytes long and I know the starting point of my array, I can jump anywhere to it really easily. Right? If I know my starting value and I know that everything is right next to each other and of the same size, it makes it really easy to jump around. And that's why with both lists and arrays, you can do, they call it like random access, right? And you all might have heard of random access memory, meaning like it takes the same amount of time to access any random part of that memory. It doesn't matter. And the reason we can do this is because it's all structured, right? So the computer knows my array starts here. Each chunk in my array is the same size, and my array ends here. So all I need to know is the starting point and which index you want, and I can do the work of figuring out where to go from there. And I want to check in here. This is a good point to pause and see what questions people have or things you might be curious about. And I also want to check in to see if this makes sense, because I know I'm getting a little abstract and jumping around a little bit here.
Is there other a value to organizing data, like kind of with consistent data types? And then also, would it be valuable to think of a tuple as more like an array, even though it doesn't hold to one particular data type?
Those are great questions. There is a huge amount of value to organizing data by consistent data types. The good news is we don't have to do that work. The Python interpreter does that work for us. That's the value of these higher level languages like Python or Ruby or Java. And when I say interpreter, what I mean is you all have probably heard of a compiler. So if I write code in Java or C, I then run a compiler program, and that creates a new file that's basically assembly code, which is looks kind of like hexadecimal. It's not meant for people to read. But then you have, I think it might be called just the C like runtime, or well, with Java it's called something else. But that's what the computer actually runs. So for a long time, whenever you were programming, there were these two steps. You write the source code, you run your compiler, which generates, it might as well be binary. It's so close to it. It's not possible for humans to really read it. And we're not meant to read it or modify it. And then you run this other program that runs that. And you can imagine how that might take longer. There are some advantages to that, but it's also longer. And so these higher level languages, Python, Java, PHP, Ruby, when I talk about the Python interpreter, the Python runtime, the JavaScript engine, they're all sort of the same thing. And what they are is they've combined those steps of reading the source code, and I think it's called just-in-time compilation, and then running it. And a lot of work has gone into writing those programs, the Python interpreter and stuff, over a long period of time to make them very efficient. And that's why we don't have to manually worry about organizing our data in memory, like by type or anything like that, because we get to take advantage of these incredibly powerful tools that have been written for us. And the truth is, even if in your Python source code you did stuff a certain way, and you're like, okay, I think I'm kind of assigning things, you don't know exactly what the Python interpreter does, because there are all these little tricks and efficiencies built into it. So it's a little bit of a black box, and it's okay for it to be that way. But that is a really good question, and it is good to be thinking about that. Does that make sense?
Yeah, I mean, I guess my takeaway on that is I don't really need to worry about it or think about it much in terms of use. But if I am writing a program and have an efficiency problem, there might be an issue with, I guess, well, I don't know that part yet.
Correct. You don't have to worry about it. I've never done a lot of like real world like performance optimization. The rule of thumb I've always heard, there's a couple. One saying is premature optimization is the root of all evil. Because trying to optimize stuff usually means making it more complicated, which usually means introducing a bug. But also because until we actually see a performance problem, it can be very hard to guess like where the bottleneck is. And so again, I haven't done a lot of this in the real world, but my understanding is really if you're seeing performance issues, what you then want to do is there's a bunch of different tools you can use to try and figure out what part of the program is running the slowest and why, and work on that. And so we really don't have to worry about that here. It is good to be aware of like how memory is stored at a lower level, and it is good to think about some of this stuff. Some of it might come up in technical interviews. There are other places. In some ways, when we get to databases, types start to matter a bit more in thinking about like how do I combine the things, but we really don't have to worry about this low level of creating arrays and putting types of data together or stuff like that. And there was another part to your question, Brian. I'm sorry, I can't remember it off the top of my head.
It was just, I guess, is it even valuable to think of a tuple as closer to a true array?
Oh yeah, great question. Short answer, no, it is not. You're right that they have some similarities, like a tuple is fixed in size, but they're really different things for different reasons, and I should double check that. Let me quickly double check here. Let's see, because tuples do you do have to use the same type of thing in a tuple, right? Or can you mix it up? Yeah, it's I see where you're going with it. I would be curious to learn a bit more, but no, it's not. And actually, this bit right here is probably the reason why, right? Everything in Python is an object. There's a tuple class. And so really what's happening is we don't do this manually. The Python interpreter decides where in memory to save all this stuff. So it probably creates like an array to stick the tuples in, but really it's a different thing. Like the you're going to see a little bit of it this week, but really like these low level data structures, like if I was to implement my version of the Python programming language, I would maybe use arrays to implement a tuple, if that makes sense. And Frank, I think I saw your hand up as well, sir.
Yes. I think maybe my question might be getting a bit ahead, but um, so I saw it was like a long time ago. There was a like it was like the different types of sorts you can do to try to like take like a jumbled up picture and make it and rearrange it so that it ends up being the actual picture. Is this kind of like the base level of like what makes those different sort methods kind of work?
That's a great question. That is getting a little bit of ahead. The short answer is sort of. A lot of like we're not going to touch too much on like sorting algorithms this week. We're focusing a little bit more on data structures, but both with these algorithms and data structures, they're all sort of like abstracted. And so for a lot of these algorithms, they're imagining you using something like an array. It's not exactly the same. So this is sort of connected to that, in that like for a lot of these algorithms, the working assumption is like I don't have lists and tuples and dictionaries and stuff like that. So in that sense, yes, if that makes sense. And again, the reason for that is a lot of this is more theoretical, and less about like being directly applied. So kind of moving on to that, actually, this isn't quite what you were asking about, Frank, because it's not talking about algorithms, but with data structures, we can see here like where some of these data structures come from and how that relates to arrays. This data structure linked list is sort of one of the classic ones to learn with this stuff. And like, if you see a data structures problem in a technical interview, probably a linked list or a tree. We're going to come back to linked lists in the course. It can be a little funny to wrap your head around, but it's valuable to see the connection between this and an array while we're talking about this. So linked lists are meant to work with non-contiguous data, sort of like you were saying, Frank. Because like if we have, let's say, an image file, which is big, right? Like a JPEG, that could take up a lot of memory. We probably can't fit that in one array. And the thing about like computers and computer memory is it's not always easy to get stuff right next to each other, because the operating system is talking to the hard drive. There's other stuff that's already stored there. There might be other programs doing work. So and since having stuff right next to each other, like having an array or having two arrays right next to each other makes stuff really efficient. Like at a lower level, like the operating system kind of and the computers kind of like protect some of that stuff, because like maybe that's where the computer stores its own phone book or its index table, right? So for bigger chunks of data like image files, we can't always be guaranteed that all that data is going to be put right next to each other. So we need to have a way to like jump around to find things. And there's a lot of ways to do that. One way is what's called a linked list, where let's say we do have like a little array here, or it can be a tuple or something, it doesn't matter. And it stores two things: a value and a pointer to another memory address. Right? Remember, we talked a little bit about pointers. We talked a little bit about, where did my hexadecimal go? Forgive me as I'm going back in time. Here we go. We talked a little bit about memory addresses. Right? Now, I don't know off the top of my head how to do it in Python, and we really wouldn't want to in Python, but I could give my program this value and say, go grab the value of whatever lives in memory at here. And in lower level languages like C and other places, that's how this works. So this idea is I store a part of what I care about, and then a pointer to the next thing. And you can implement all sorts of interesting things with linked lists. You can implement a Python list if you wanted to with a linked list. And so here is, again, this diagram drawn out. And so you could imagine if we have something maybe that's too big to fit right next to each other, or maybe we just don't want to or need to put it like right next to each other in a series of arrays, we can use this data structure called linked list, where for each node, one cell holds a value and the next one holds a pointer. So maybe each of these is 1 byte, right? That would make sense, like 8 bits. And so our first element in our first node in the list holds the value 1. It points to the location in memory where the second one lives. So these are not next to each other, right? It's like if I'm jumping around on a vinyl record, but somehow I know where to go for each next jump. And then this holds the value 4, and then this pointer points to another spot that holds the value 12, points to some other spot, and so on and so on. And then over here, when we get to the end, there's just 0 or null or something, and that's how our program knows that we're at the last node in the list, in that the pointer, the value that's supposed to point to the location in memory doesn't point to anything at all. So just like with an array where you need to know where an array starts, we do kind of need to know this first node in the list. right? This is the first link in our chain. Once we get this, we can go through it. What I can't do here is in an array, I can jump to any one of these really easily because I know my starting point. I know how big each of these little chunks of memory is. They're all the same size. So I know if I want to go to index 3, I just add like 16 to whatever this starting value is, this like memory location or whatever. I can't really do that with the linked list. I kind of have to go through it in sequence because while each of these might be the same size, I have no idea where the next location in memory is. So let me just pause here and see what questions people have or what's on people's minds.
Hey Adam, so you said this is all happening like under the hood? Like this isn't something that we actually like do or
Yeah, that's a good question, Anthony. So linked lists, we're going to come back to them later this week. Today it's more of a preview, but linked lists and these two other data structures, stacks and queues, we will practice implementing. And there's two reasons for this. One is really sometimes it comes up in technical interviews. And the other is this is sort of the classic, like, this is sort of like the entry level. I think it's like the entry level computer science course might be like writing simple programs and object oriented programming. And then the next class that everyone takes is data structures. So this is sort of like the common knowledge. So you all will implement like a simple linked list and a stack and a queue. But then the thing that's a little different about this data structure stuff is you won't be reusing it over and over in the class. That said, the concepts are useful and the concepts do show up in surprising ways. And that's kind of why it's stuck around in the curriculum. Does that make sense?
yeah. So like I don't know if I missed it, but like is it like more of an abstract thing or is it something that you actually like write out?
Yeah, let me in fact, let me just go ahead and show you. Okay, I
Thank
see.
you.
Totally. Data structures. Okay, yeah, that's not a bad chart. Lost my slide deck here, but and it is a little weird because again, unlike most other things in the class, we are going to learn to implement a linked list, but there's not going to be like a direct application of it when we're building our personal projects or anything like that. So I kind of talked about this slide already about why it matters. I think again, the analogy here to use is like my doctor for my annual physical isn't going to be like doing like, well, soon they might be doing DNA scans or whatever, but they're not like a geneticist, but I would still want my doctor to kind of know about DNA. So again, we'll come on, I think it's Wednesday, we'll spend more time with linked lists. This is a bit more of a preview because it's a nice contrast to an array. But if you were to implement a linked list, it's pretty simple. And let's see here. So I do apologize. I think a little bit of this is actually, we might need to add a little bit more, but I'll just build this in a sec just so we can see it as long as we're talking about this. Yeah, in fact, let me just go ahead and build this real quick because I think that'll be even easier than just talking about it. And I'll shift this over to our demos and notes. Can everyone see my screen, by the way?
Could you make it just a little bit bigger, please?
Totally. And then after this, we'll take a quick break. And just for teaching purposes, I'm probably not going to add getters and setters here. So without even worrying too much about like the whole linked list part, like this feels pretty comfortable, right? We've made a class, we can give it a value. Again, it really is best practice to use getters and setters, but for teaching purposes and time and simplicity, I'm going to not do that at the moment. So instead of my node, let's call this the head of my list. And think about the head and the tail of a snake. Think about the beginning and the end. So this is the head of my list. And let's just create some other random node and do head next equals some node. And we can do something like while let's do not at tail equals, or let's do end of list. How about node next node? And I think I'm almost done with this. Let's see what we do not like here. So I probably got some things wrong here. Let's see what we don't like. So that's fine. That's Python saying, thinking this is a constant. This is me being used to JavaScript. And then over here, all right, we'll make, just to make the squiggly go away, we'll make Python happy, even though it's not really a constant. And let's see if I got this right. And I very clearly did not. So let's, and I see my problem. The problem is that the while loop looks at that, and I had my booleans flipped. But in fact, let's just name it like this. And I apologize, I've gone a little off track here. But there you go. And in fact, why don't I just split this? And then we can kind of look at what we have going on here. And we can then look at our loop over here. So this is relatively straightforward to write once you see it, right? I create this little class, it holds a value of itself, and it points to the next thing. You could implement this with a dictionary. You could implement this with a real array if we were writing in a language like C. We need the head of our list. We do have to keep track of that. And we need some way of creating these other list elements. And I just sort of contrived this, right? And then we need to be able to add them. And that's stuff that we'll kind of learn later. And you can sort of see how doing this, it's like, no, I'm not working with arrays and real computer memory, but dealing with this sort of classic data structure sort of forces me to pretend as if I am. Because I have to keep track of pointers and things like that. Like I have to keep track of if I'm at the end of the list or not. And I had that kind of confused because I said it before I had a different and set it to false, but then I never went into the while loop. I need a pointer that points to where I am in the list. And then I need to check and say, hey, does this node point to another node? If it does, let's move forward. Otherwise, we're at the end of the list. So again, on Wednesday, we'll spend more time on this, but I just wanted to sort of like at least demo this code today. And so Anthony, to answer your question, this is sort of like, yes, you all will like implement a linked list along these lines this week. And how are people feeling about this? Because I know I dove around a bit.
Thank you.
Totally. And to go back to the diagram, this is really what we're doing, right? Even though we're using like a class and stuff, we're having a way to connect things where it's not necessarily all right next to each other. And even if we're not like writing linked lists all the time, there's some value in that. So I'm curious what questions people have. And I would like to know what people's overall kind of comfort level is with this code. Again, this is just a little bit of a preview. We're really going to go into this more in depth on Wednesday. But I would love to know what questions people have kind of about this while we're looking at it. Okay, cool. So this is really, I think, the key bit here, what I wrote. We talked a little bit about arrays. We kind of can see how arrays might have limitations. I have a huge JPEG file that can't fit all one after the other. How is my computer going to store it at a low level? Maybe we use something like a linked list. Again, the reason that we're learning these data structures is twofold. One is they may come up in technical interviews, and the other is these are really the building blocks of how computers work. So there's value in knowing that even if we're not directly using it, and also because you do see some of these concepts come up in surprising ways. Like I might not implement a linked list, but let's see if I have an image carousel that we could like, here we go. Oh, I really wanted to. Let's see if we can find a slider. Here we go, perfect. So this slider we might not really use a linked list to build this, but where do these images live? Do they necessarily live next to each other? How does the browser know to get them? Maybe the way this works is there's a little bit of JSON that has the link to the first image and the link to the next image. Maybe it's sort of implemented as a little linked list, or maybe it's a normal list, like an array or something. But the point being is, this is a useful pattern to be aware of, even if we're not directly applying it, and that's why it's, I think, kind of stuck around in computer science curriculums. So again, this week is a little different. This stuff isn't as much directly as applied, but it is sort of fundamental knowledge, and sometimes it pops up on interviews, and it also gives you a common language to talk with everyone else in the industry about stuff. So this is a great point to stop because I've been going on for a while. I'm thinking maybe we should do like either a 10 or a 15-minute break.